Yeah.
And when I was in the Netherlands, it was like 20 bucks.
Right. Morning, everybody. Welcome back. Thin films. We are. I did post the. Help me with the word. Information about the exam. Topics. I posted the topics for the exam this morning, so you can go on there and see that. I want to switch this. I want to show you some more videos of like thin films, how they work, what's going on, why they're so awesome, all that kind of stuff. So just a couple of videos here. And check the audio. It wasn't on. There we go. Go. Soap bubbles are awesome.
If we dip this cylinder into a soap solution, a thin flat film is placed on the mouth of the cylinder. We'll shine the light off the soap film and onto the screen to show how the colors we see depend on the thickness of the film. Immediately after the film is produced, the colors are pale and difficult to see.
It's thinning up at the top.
As the fluid drains to the bottom,
It's getting thicker at the bottom.
and the colors become more distinct.
So this thin film of soap and water is causing different frequencies and wavelengths to be seen. What's that black line at the top? If it's black, what's going on? Constructive or destructive?
So thin at the top,
Yeah, it's got to be destructive.
leaving a dark space where almost no light reflects.
Right, that's a destructive phenomenon up there at the top.
Finally, the film breaks.
It was sad. So sad. Okay, this one we'll talk about after I show it to you.
When two transparent plates are pressed together and viewed in a bright light, interference patterns can often be seen. We'll use this monochromatic sodium light and two large glass plates to demonstrate one type of pattern.
Monochromatic, one color.
Just one glass plate in place, the reflection of the sodium light is uniform. When we add the second plate, an interference pattern appears. The pattern shifts as the flexible pieces of glass relax into position. Squeezing down on the plates causes a shift in the pattern.
So changing the thickness of that air layer that's been trapped between the two plates of glasses causes that pattern to shift. Why would I show something like that? If you've ever put a screen protector on any of your devices, okay, this was something that plagued us like 5 years ago or more. But sometimes you would get air trapped underneath there. And I'm not talking about that little bubble that was always so annoying and you couldn't get out no matter how much you squeegeed it, right? I'm talking about like if you held it up, you could see almost that rainbow, these circular patterns forming because you had trapped a very thin layer of air underneath the screen protector. Nowadays, the glass and tempered glass and other plastics that they use for these screen protectors, they have the ability to outgas or to let gases sort of permeate through the glass. And so after like 24 hours of putting it on, usually like the bubbles are kind of gone and you don't get this pattern anymore. But thin films are everywhere, right? And we are going to continue to figure out how to deal with this. Well, okay, so rules. What were the rules? Let's write some of these down, right? If you go from N low to N high, what happens to the phase? It shifts. Shifts by how much? 180 degrees, right? Okay. And if you go from N high to N low, I usually say higher to lower, right? Or lower to higher, something like that. Then there is no shift. So in developing the equations for thin films, I warned you last time that every problem you need to actually not develop the equations, but you need to understand what the equation is going to tell you for a given situation. So let's do that. okay, and see where we get. The first thing I need, so this is a rule that we need to live by, okay? This is a little bit of a tangent, but an important one. The wavelength of light changes when light enters a new medium. Remember that the speed of light, I should have used c instead of v, is equal to wavelength times frequency. Speed of light is determined by the medium in which it travels. And if we go into a new medium, we use the index of refraction to tell us what that new speed is going to be. We can solve for that new speed. But as that speed alters, wavelength and frequency could also alter, right? It could be both wavelength and frequency that are doing it. It could be one or the other. And we know that it's wavelength that changes, but not frequency. That's because frequency is color. When light passes through a clear window, does its color change? Do like green things become red or blue things become orange? No, we don't, there isn't a shift, unless of course like the pane of glass is tinted or something like that, right? But a nice, clear plane of glass, transparent piece of glass, doesn't shift the frequency, doesn't change the color of the light that goes through. Red light stays red, blue light stays blue. It's all very consistent. So if the frequency is constant, but the speed changes, that means the wavelength must be changing also. And that's what we found by investigation and observation. So the wavelength of light in any material is going to be the wavelength in vacuum divided by the index of refraction. So if you got light of 550 nanometer wavelength, and that's what it is traveling in vacuum or air, we can tell you what the wavelength is going to be in glass that has an index of refraction of 1.5, right? You just take that wavelength, 550 nanometers, divide by 1.5, and now you have the wavelength in the material. Lucky for us, we're not going to have to deal with like actually calculating those wavelengths, because we're going to do a little bit of a substitution trick that's going to help us. But I just wanted you to understand that light is doing something as it enters these thin films, right? We're moving into a different material, and so the wavelength's going to change. All right, back when we did the double slit, where was that? This is this horrible, right? All this stuff going on and yada, yada, yada. But we learned some language here, right? We learned about path length difference, the extra distance that one wave travels compared to another. We learned about these conditions, constructive and destructive interference, and kind of the language of using like fractions of a wavelength shift in order for those phase shifts to happen. We're going to apply exactly that same idea and even some of the same terminology to what's going on in thin films. You can write down what I finally write down in the boxes, right, if you want that in your notes. But just to kind of get there, right, we are going to have our path length difference equal to condition. This is what we did when we did interference for the double slit. But now we're going to apply it to the physics of the thin film. There are two rays that are coming off of this surface. There's this first reflected ray right here, and then there's this second ray that comes down, bounces off the bottom, and comes out. First one bounces, second one travels extra distance to get to the bottom of the layer, bounces off, and comes back up. The path length difference is what I've traced right here. Okay? This is the extra distance the second ray travels compared to the first. Now, again, we've drawn We've drawn it wrong, but we've drawn it for clarity. I cleverly erased the picture that I had before, right, where everything's straight up and down, right, where it's really hard to tell what's going on. So we've got to realize it's really what we're talking about is straight up and down. The thickness T of the film, right, is the thickness of the film. So thinking about the straight up and down case, what would the extra distance be for a ray that comes straight down and then comes straight back up again? 2t, right? So our path length difference is 2t. And then we have our conditions, right? And the conditions can either be m lambda or they can be m plus a half lambda. Do not jump to the conclusion that m lambda means constructive, because in the thin film case it does not, and I will demonstrate this later. I just want to warn you, with the double slit, m lambda is constructive. M plus a half is destructive. That's set in stone. That's not going to change. But with thin films, it changes. Let me see if I can help you understand why. What about the wavelength in the material? Really, this would be lambda, the wavelength in the material, because we're talking about a path length difference in the thin film. And so we need to know the wavelength in the thin film. Luckily, we can just substitute, because this is just lambda over m, n as in November, m plus a half lambda. We can do that. But physicists, we just don't like fractions. We never have. I've never really met a physicist that went, oh, goody, fractions. Most of us are just like, we never liked fractions in school. So what we will do is we will alter this equation just slightly and multiply both sides by n, just to get rid of that denominator that's right there. So what you'll see written quite often, maybe not in your book, I think your book does this slightly different, okay, is you'll see the equations 2nt, see how we brought the index of refraction over, right, equals m lambda, and then 2nt equals m plus a half lambda. Those right there, okay, are the equations that we're going to need to use to figure out what's going on with this film. But again, m lambda does not mean constructive. M plus a half does not mean destructive. So let me tell you what these equations, I never get this vocabulary right. These equations say something specific, but their meaning changes depending on the physical situation we have with the thin film. What do I mean by that? This first equation right here, this is very important. It says, do nothing to the phase relationship. In other words, we're going to figure out the thickness of the film that will cause a path length difference such that the extra distance is a multiple of the wavelength that was there already. That was a lot of words, and I know it's hard to understand. But just hold on to this idea, right? That 2nt m lambda says, don't do anything to the current phase relationship. Hold that thought. This one says, change the phase, we'll just do it shorthand, change the phase by 180 degrees. Specifically talking about the second ray, because that's the one we have control over, because it's the one that's traveling through the thin film. But m plus a half, you need to get into your brain that that's saying, I'm going to change the relationship between these two rays by 180 degrees. So that's what they say, but what they mean changes depending on the problem. And let me start doing examples and trying to tie all of this information together. Okay, let's review the information we've got. We know that waves change their phase depending on how they bounce, right? Low to high, high to low index. There's these rules that I've got in that top box, okay? And then we have the physics of interference, path length difference equals condition, playing out in this thin film, but we can't assume constructive and destructive interference just from the equations. The equations are telling us maintain the phase relationship that's already there or change the phase relationship by 180 degrees. And now let me do a whole bunch of examples, okay? So in the two that I've got here on the screen, what is going on in this one that's right in the middle? If we left the entire system like alone, if we did not alter the phase relationship between these two rays, would this be constructive or destructive interference? We have one ray that's 180 degrees in its phase. We have the second ray that's 180 degrees in its phase. What's the difference there? 0, right? There's no difference between those two rays, which means they are peaking and troughing at the same time in the same place. So what are we going to get? Constructive. If the two phase angles are identical, then it's constructive interference. It doesn't matter what the actual number is. All that matters is, are they the same or are they different? In this case, the two phase angles are the same, which means they will be naturally constructive. So that means that 2nt, m lambda, which says do nothing, don't change this phase relationship. What will this equation then mean? Is it the constructive or destructive equation? It's the constructive equation because we're doing nothing to a 180-180 relationship. What does this second equation say? Change the phase by 180. In other words, come over here and add 180 to the second one. So now what do we have? We have 180 and 360. Are those different? Yeah. They're 180 degrees out of phase. And so this is going to be destructive. So this one says don't change. This one says change by 180. And in this problem, this one becomes the constructive, and this one becomes the destructive. Compare and contrast that to this one. Again, we did this last time, but the reason we have 180 on there is because we go from an index of 1 to an index of 1.33, right? We're going from a low to a high index of refraction material. So the wave, when it bounces, changes its phase by 180 degrees. But when we go through the film and go back to air, right, through the water film back to air, it's a high to low change. So therefore, there is no phase change. And that's why that second one comes out as 0 degrees. Okay? So, if we leave this relationship alone and we don't change anything, what does this equation now mean? It's now destructive. And if we then change the second one by 180, now we have constructive. They're both the same. So right there, I gave you two examples where the equations changed their meaning on you, right? Whatever you do, do not lock into your brain that m lambda is constructive. That's only true for the double slit, right? But in thin films, we have to look at the physics of what's going on in the problem and then determine, based on what the equation tells us to do, we have to determine whether it's the constructive or destructive case. All right. Let's just knock out some examples here, okay? So every thin film problem, right? You have the film, you have light coming in. I used to just draw it like that, okay? So let's see. We'll do air. Give me either a material or just a number. 1.33? Okay. And then we'll do 1.52. So air to water to glass. This is a thin film of water sitting on top of glass. Okay. What's the first ray going to be? What's its phase? We're going from low to high. So we're going to write down 180, right? All right. And then 1.33 to 1.52, what's it going to be? Also 180. So if I leave everything alone, excuse me, and I don't change anything, what do we end up with? Why is it constructive? They're both 180. They're both the same, right? So this is my constructive equation. So what is the other equation going to be? The one with the half in it? This will be destructive. All right. Let's do, again, we'll do air. We'll do oil. And then we'll do water. So this is an oil spill. Why would we want to why would we want to know the thickness of an oil film on water? Let's say, something went wrong with a wellhead in the Gulf of Mexico, right? BP lost its. I don't know if you guys remember. Were you too young for that oil spill? Huge oil spill, right, in the Gulf of Mexico. There was the Exxon Valdez in Alaska when I was growing up, right? Big tanker, ran aground, spilled a ton of oil, right? In order to know how to clean it up, you need to know how much oil has been spilled, so that you know how much surfactant to order, which is a thing that breaks down the oil and makes it easy to suck up. You need to know how much oil-eating bacteria to release into the ecosystem, right? There's a bunch of reasons why you need to know how much oil has been spilled. If we can figure out the thickness of that oil on the surface of water, and we know the surface area that the spill takes up, we can now find the volume, right? We know the area. We've measured the thickness. The volume will just be the area times the thickness. And now you know how much oil has been spilled. You know how much chemicals you need to order to fix the problem. You fight chemicals with chemicals, apparently. So the way this works in practice is that during an oil spill, they'll come out with these handheld measurement devices that you point at the water. You try to get it straight down, but it can also handle angles. And you hit the button, okay? It sends out a beam of light. It sees the reflections. It measures whether it's constructive, destructive, all that kind of stuff. And then it reports back the thickness of that sample. It's literally just a light laser gun, right, that tells you the thickness of the film on the top of the surface of the water, okay? You do that, you sample 100, 1,000 times in different places, you get an average thickness. Bob's your uncle, you know how much oil is sitting on the surface of the water, right? So there's lots of practical applications, and I'll keep bringing them up because I've done most of them. Okay, so what do we got here? What's the phase of the first bounce? 180. How'd you know that? High to low, right? We went from 1 to 1.4, right? You said it wrong, but we got it right, okay? But now we're going from 1.4 to 1.33. What kind of transition is that? It's a high to a lower, isn't it? A bigger number to a smaller number. So what's that phase change going to be? 0 degrees. All right. If we leave it alone, if we don't change this relationship, what will we end up with? Because it's 180 and 0, isn't it? But if we change it, yeah, it's supposed to be an equal sign in there somewhere. Now what do we get? If this tells us to add 180, then what do we get? 180 plus 180, we get the same thing. This is going to be our constructive case. This is what you have to do for every problem. Okay? You have to figure out what the phase changes are, and then you need to apply the equation correctly to determine whether it's constructive or destructive. For every problem. My advice, draw the picture, put the phase changes on it based on the indices of refraction, write down the equation, specify what the equation means. Does it mean constructive or does it mean destructive? Do not lock in, right, and assume that it's going to be, m lambda is always constructive, because it's not going to be. You'll only be right 1/4 of the time. Okay? Technically 50-50, but there's lots of different possibilities for this. Okay? All right, so let's do some examples. So, by the way, that part of the problem is all set up, because now we have to figure out what they're asking for. Sometimes they tell us thickness and they want us to find index of refraction. Sometimes we know the thickness and they want us to find the wavelengths, right, that are happening. Like, there's lots of things to kind of solve for once you've figured out the correct application of the equations, right? Figure out the physics first and then figure out what they're asking us to do. Okay, so first step, you have to visualize the thin film structure. And again, that structure is always superstrate, film, substrate. So what I draw, again, is I just draw 2 lines, right? And between the 2 lines is the film. So what are they telling us? This first number, n equals 1.33, what are they trying to say? What is that the index of? The film, the substrate, superstrate, what is it? It's a soap film. So where do I put the index? Do I put it here? Do I put it here? Do I put it here? This is the index of the film, isn't it? It says a soap film of index 1.33. So that means our thin film is this one. And it says it's in air. So what's on top? Air. What's on bottom? Air. The film is in air, right? So what is this physically? It's a bubble. We're solving the bubble again. Okay? Now, we've kind of already done it over here, haven't we? We got the 1.331, but let's go through the process, right? So we've kind of laid out the structure. Then we do I always think of them as like 2 check marks, right? You're doing that one, and then you're doing that one. It's just you're attaching them to each other, right? Okay? All right. Physics of the situation. Off the top surface. Phase change or not? Yes. We're going low to high. And then bottom surface, high to low. Nothing? Okay. So 2nt equals m lambda says don't change anything. So we're going to end up with destructive. 2mt, m plus a half lambda means constructive in that case, right? Because the second one says change the second ray by 180. If we did that, if we added 180, we would have 180 and 180, it would be constructive. But we've already identified which one's the destructive, so the other one has to be the opposite. There's only two choices. That, again, you do that the same for every problem. Now, I'm going to start trying to figure out what the problem's asking me to actually do. Okay? This I have to do every single time, but from here on out, it's a variations on the theme of whatever it is they're asking me. Okay? They give me some clues, right? Like the 652 nanometers. What is that? You can tell from the unit that it's the wavelength. Okay? It says constructive interference in red light. This is the wavelength of the light that's shining on the film. So my wavelength is 652 nanometers. This is interesting. They told me it was constructive interference for this wavelength. So which of these two equations apply for this wavelength right here? The constructive case. Well, which one's the constructive case? It's this one right here, isn't it? However, which wavelengths destructively interfere? So now if they're asking me about destructive things, I have to be using that one, don't I? So which one do I use? Yeah, I got to use both. Because what is it that I need to find? They told me the wavelength, but they really told me nothing else. So I know my wavelength. We'll talk about M in a second. We know our index here, right? What do we not know? Thickness. So we can use this first equation, this second equation, right? The constructive interference in this wavelength. We can use that together to find the thickness. We do that in more permanent ink here. The constructive interference, which is this wavelength right here, we are going to use this equation for. Why? Because I'm guessing or because I know? Because we know. You guys might be guessing tonight when you're trying to do your homework, but right now we know, right? And how do we know? It says constructive interference, and we've determined which of these equations is the constructive equation. So my plan is do the purple box to find the thickness of the film. Once I know the thickness, does the thickness change whether we're using constructive or destructive interference? No. The soap bubble thickness stays the same. Okay? And so we can use that thickness then to solve for the wavelengths that they're asking for in the other side. I still don't know what to do with M, but let's see where we can get. Okay? So we're going to use 2nt equals m plus a half times my lambda. You're welcome to throw in numbers right now if you want. But we do need to deal with this m value. This m value, like what is it? What is it used for? Do you remember from double slit? It was just a number. What kind? It was a special kind of number. What kind of number was it? It was always an integer. 1, 2, 3, 4, right? It was never a decimal or anything like that. It's like a counting number, right? It's a multiple. It gives us like multiples of the wavelength, multiples of the pattern, all that kind of stuff. And so in the case of thin films, it's telling us, right, that we could have multiple answers for the thickness. As long as the thickness of the film hits a half wavelength multiple, it's going to have constructive interference. That's what that equation's saying. But the problem gave us a clue as to what m value we need to pick. Does anybody see the clue? Minimum thickness, right? Okay. How do we make t as small as possible, right? We're solving for t, which is going to be m plus a half lambda divided by 2n, right? What value of m do we pick to make t as small as possible? And what's the smallest m we can put in there? 0. I know. It's a little bit tricky. Right? But we can put 0 in for m. As long as there's a half, you can use 0. If it's just m times lambda, you can't put 0 in. I mean, technically a 0 thickness film would cause something to happen, but usually nothing to happen. Okay? A 0 thickness film means the film doesn't exist. Okay. So if we let m equal 0, then our t is just going to be lambda over 4n. You see what happened there? 0 plus a half is a half. And a half times lambda divided by 2n is lambda over 4n. In thin films physics circles, we call this the quarter wavelength limit. In other words, you can guess at what thickness you need to pull something off, and you'll be right half of the time if you guess a quarter. The other guess, by the way, is a half. So anyway. So now we can go ahead and chuck stuff in. Do I have to convert my lambda into meters? What are the units of the numbers on the bottom? Nothing. The units of 2 are nothing. The units of the index of refraction are nothing. It's unitless. It's a ratio, right? And so the units cancel out. So I can take my wavelength in nanometers, divide it by nothing units, and still end up in nanometers. You can convert it to meters if you want, but that's doing extra work. This is going to be 652 divided by 2 times 1.33. Which I don't have written down anywhere on my page. Why am I not doing the examples? 4. 4 and 2 are the same number, by the way. 4. Would you get 122.5? We'll just call it 123. Nanometers. Okay, so what is 123 nanometers? It's time. No, it's thickness, right? It's the thickness of the film. I'm going to warn you about something. I think thin films is one of those cases, and I know you felt this in other places in your physics career, where it all makes sense when Mr. Balogh's talking about it. Like right now, you're like, oh, yeah, okay, yeah, good, I'm doing awesome, right? I'm picking the right. You're gonna go do your homework. What's gonna happen? I've also noticed that ChatGPT gets this wrong a lot. Like for whatever reason, thin films, ChatGPT just seems to be guessing, right? Again, there's no knowledge driving ChatGPT. It's just picking words that are statistically end up close to other words, right? And when it comes to the math, it can just be wrong. Again, it has a 50% chance of being right, and in this case, it's 50% of the time it's wrong. I haven't tried it recently. I haven't tried it this semester. These things change quite quickly. All right, so now that we know the thickness, what do they want us to find? What wavelength? Oh, geez. With an S. What wavelengths would destructively interfere? So we're using the destructive equation, right? M lambda. What are we solving for? Yeah, we're solving for lambda. What wavelength? And why are there more than one? Let's figure this out. 2nt over m equals lambda, right? So that's 2 times 1.33. Again, the index of refraction in this equation is the index of the film. Whatever the film, you can have a lot of indexes of refraction flying around in some of these problems, right? You have up to 3, right? Indexes of refractions flying around. Make sure that the n that you put into this equation is the index of the thin film, not the superstrate, not the substrate. Okay. And then the thickness is 123 nanometers, and then it's divided by m. Okay, so let's just do a little bit, because the thing on the top is a number, right?
Yeah.
What's the number?
327.
327 nanometers? Okay. Divided by m. They said wavelengths, plural. Is there more than one wavelength in this answer? Yeah, because what's m? It's a counting number, right? It's this multiple number. And it can be, well, it can be anything except, in this case, can't be 0, right? Divide by 0 error, right? We just broke the universe. So as long as we start at 1, we can go as far as we want, right? So there's multiple answers here, right? So, whoa, that was not an F. 4, m equals 1, lambda 1 will be 327 divided by 1, or 327 nanometers. Is that one in the visible range?
No.
What does it say about the visible range in this problem? 400 to 700. So that one doesn't fit, right? Okay. You go solve what? For m equals 2, that's going to be 327 divided by 2. I don't know what that number is, but we are going the wrong direction, right? Because this is a number that's less, less than that number, right? And if we do m equals 3, that's less than that. We're going the wrong way. So how many times do I have to do this to figure out what the answer is? Divide by a half. Why am I dividing by a half?
Can't you divide by half?
No.
Be half?
M cannot be a half.
So it doesn't exist?
M is 1, 2, 3, 4, 5, 6. It's an integer. Can only be an integer.
What?
Yes. And if you have m plus a half, m can be 0. Right? What? It could be you could have negative m's if you wanted. But it's just a reflection of what's going on around 0, right? It's just m lambda you can't have as 0 because, well, there's no thickness there, right? But here, because we have that half, we can start with 0 as our counting number. But again, m is an integer. You're not free to pick whatever you want m to be. You're free to pick as long as you only pick integers. You could put m equals 1,000,000 in there for all I care, right? And get an answer. But that answer is always still going to be smaller than 327, isn't it? Yeah. So what's the answer here? What wavelengths? 0. There are no lambdas. That's my answer. How you doing?
Cool.
It's not that bad yet. Okay? Because you're going to do your homework and you're going to be flying solo and it's going to be rough. Hold on to this process, right? If you have to come back to this part in the YouTube video, your process is draw the situation, determine the phase angles, figure out what the equations mean. They always say the same thing. M lambda says, don't change anything. M plus a half lambda says, change by 180. They always say exactly the same thing. But what they mean, constructive and destructive, changes based on what you did in this first step. Once you have that all laid out, then you can begin figuring out what the problem's trying to get you to do. Does anybody have a $20 bill? I realize I am asking a room full of students if they have money. But does anybody have a $20 bill? If somebody has a $20 bill, I will stop what I'm doing right now. No, it's not. I just need I need a $20 bill. And I promise you will get it back. Truman has a 20? Okay. So let's make sure the Elmo is, I don't know if this is going to work. I don't know if this is going to work. So if I can get it to work on the Elmo, great. If not, okay. All right. I would like everybody in this room to witness that I'm taking $20 from Truman of his own accord, and that there are no material exchanges happening because of this transfer of money. Is everybody very clear here? There's no bribes going on. And Truman will get this $20 bill back in less than 5 minutes. You guys want to write down the serial number? No? Okay, all right. Let's see if I can get it to appear on the Elmo. Okay? On the $20 bill in the United States of America, okay, there is a security device. You see that 20 right there? Yeah. Okay? It is printed with an ink that is a thin film. If you take a $20 bill and you rotate it, did you see the color change? Yeah. Do you see how it starts off kind of yellow goldish? And then as you tilt it, it goes to green and black. This looks a whole lot better in person than it does on this Elmo. Okay? So the next time you have a $20 bill, which is sometime after you graduate and get a job, take a look. Okay? I really shouldn't make jokes like that. Grab the $20 bill and rotate it. You'll see it go from yellow to green to a kind of blue and back and forth again, right? That ink is engineered. Truman, do it. And Truman, assert that I gave you your money back?
Yeah.
Okay, all right. Is it the same bill?
Yep.
Good, all right. And would you now describe what you're seeing to the audience?
Yeah.
Yeah.
Pretty cool.
It's pretty cool.
It's even on the equal too.
Yeah, there's different parts of the bill, okay, that have this ink on it, but it's the 20 that's really easy to kind of see it, okay? And so this is how, I should stop recording right now. This is how you counterfeit money, right? No, don't do that, right? There's other security features in the bills, okay? This ink, I think, it first appears on the 20, I think it's on the 50 and the 100 and so on and so forth. It's a little bit more expensive to kind of pull it off, and it's not worth it for the ones in the 5s and the 10s. I think it's the $100 bill where it starts. There is a strip. Yeah. And so sometimes you'll see a cashier or a teller, they'll hold a $100 bill up to the light just to make sure that the security strip is sitting where it's supposed to sit. And there's other ways, if you handle money as a cashier or anything like that, they'll teach you how to very quickly identify a counterfeit bill from one that isn't, right? But there you go. Thin films right in your pocket, right? Thin films on our money. Thin films on our glasses. Thin films on our cameras for our cell phones. If you look at the glass on the back of your cell phone and you hold it up to the light, you'll see the color change. Assuming you don't have a screen protector over it, okay? You'll see the color change in that lens, the little tiny part down inside, okay? There's a thin film that's been applied there to be the anti-reflective coating that helps avoid all kinds of visual artifacts in the pictures and videos you take with your cell phone. Thin film transistors in certain flat panel displays. Why did they call them thin film transistors? Okay? This stuff, thin film physics, is literally everywhere. This is one of the reasons I got into it, right? As an undergraduate and graduate student. I was looking around for physics that I could do for the next 4 years of my life that I felt would be fun to do, exciting, and have some practical application to the world at large. In some sense, I was a little bit more engineer than physicist. It's just I didn't want to be legally bound by any of the work that I did, so I wanted to stay in physics. So I wandered into the experimental physics area of my college. There were two grand sort of divisions in the physics department. This is always the case everywhere. There's theoretical physics, where you get to sit in your office all day long and do math. This was not something that sounded good to me. Okay? Or there was experimental physics, where you didn't really have an office. What you had was a lab, and you lived in it, right, to do all of the experiments. That sounded a little bit better. In all honesty, the thing that sounded the best was out hiking every day, but there were already too many biologists in the family, and I couldn't stand it. So I went into physics. So yeah, in my family, there's 3 like professional biologists and a bunch of closet biologists. My mother, retired biologist. My sister, doctorate in evolutionary ecology. And my brother-in-law, married to that sister, he is a herpetologist. Does anybody know what that means? Herpetologist. Studies amphibians. So frogs, salamanders, snails, I think, belong in herpetology. Anyway, going on a hike with my family. You can't get 30 feet down the trail before somebody has identified all the flowers and plants. My sister is giving me like all the mitochondrial DNA information about where it came from. My mom's identified everything. My sister's told me about all the DNA. And my brother-in-law has turned over like every rock and log that he can find, right, looking for herps. And the first time I heard that, he's like, do you want to go herping? I'm like, dude, we need to sit down and have a talk if you're dating my sister. He's like, no, we're going to go find snakes. I was like, we need to have a talk. No, I love my brother. He's amazing. Amazing man, amazing scientist. Anyway, let's do this. Okay? Let's do this. Okay. Structure. Always start with the structure. 2 lines and 2 check marks. Right? Where's the film? It's in the middle. Do we know anything about the film? Yeah, we know it's index of refraction. Okay? But we have to know something about the top and bottom. What is this film sitting on? Water. How do we know what the index of refraction of water is? We go look it up. Or if you're me and you've done this so much in your life, you remember that it's just 1.33. I'm really bad at numbers, but I'm really good at indexes of refraction. I think because most of my graduate work was measuring index of refraction of these things. Like we had to characterize materials all the time. But we didn't usually use water. I don't know why water stuck. Uranium, I know it for uranium, silicon, ytterbium. Anyway. It can't, well, no, I'm not sure what you mean. It's the material that makes pottery glazes look orange. If you got an orange pigment in a pottery glaze, there's a good chance it's got uranium oxide in it. Yeah, that's orangish.
Uranium glass, though.
But uranium glass, I don't know. You talking about the glass that's used to protect you from the radiation that uranium gives off?
Like teacups.
Oh, I don't know.
Sorry, I digress.
I generally don't put uranium in my food products. We need to have a talk. So, what's going on in this film? What's the first bounce? Thank you. What's the first bounce? 180. Why? Low to high. What's the second bounce? 180. Low to high. 1.25 to 1.33 is a lower to a higher. Okay. If we leave it alone. Notice, I wrote down an equation, but it says if we leave it alone. Right? If we leave it alone, then what do we have? Constructive. They're both 180. They're both the same. They're going to be liking each other. 2nt equals m plus a half lambda. Therefore, will be my destructive. Just because I already know the other one's constructive, the other one has to be destructive. But also, if I add 180 to that second one, I get 360. And 180 and 360 are not the same thing, and so therefore, destructive. Okay. I haven't really read the rest of the problem. That's a lie. I've done this problem a lot over the years. But I'm trying to just show you, you can get a lot of traction into the problem without ever even understanding what the problem's asking you to do. Right? So now let's parse what the problem wants us to do. Okay? What are they asking us to find? What is the thickness? Right? So we know we're solving for what symbol? T. Sometimes I do like to just kind of go, that. Right? Like that's what I'm going for, right? But how do I know which of these equations to use? I've got two. I suppose I got a 50-50 chance, right, of getting it right. But I would like to be 100% sure. How do I know which of these equations to use? It says absent, right? A certain wavelength is gone, is absent, is destroyed, is dark, is missing. This is deconstructive, isn't it? This is where they'll try to trip you up, right? With the vocabulary. Okay, so that means that because we are talking about an absent reflection, that means we're using the destructive equation. Right? Again, we're solving for thickness. So that's 2nt equals m plus a half lambda. Do we know the lambda? Did they give us the wavelength? Yep. 521 nanometers. So I have my index. I know what 2 is. Oh, m. As in Mike. What am I going to pick for m? What could it be? 0, 1, 2, 3, 4, 5, right? As long as it's an integer starting with 0, because we're in the m plus a half one, so we can pick 0. So how do I know which one they want? It says minimum thickness, right? And so again, to minimize this thickness, I would put 0 in for this m. 2 equals lambda over 2, so the quarter wavelength. So that's going to be 521 divided by 4 times, what index do I put in? This screws up newbies all the time. It's the 1.25, good. Why is it 1.25? It's the film, right? It's the film that matters. Superstrate, substrate, they just tell you what's going on for the first part where you figure out the phase changes. But in these equations, n is the film's index. I don't know what this number is. 104 nanometers. Boom, we're done. I now know I have about a 100 nanometer thick slick of oil. If I know that that oil is taking up, say, 6.5 square kilometers of surface area on the ocean, I can figure out how much oil was spilled. I now know how much surfactant to get or bacteria to buy or whatever. Okay?
Wait, so if bacteria eat oil, then what do they excrete?
They poop out. I can't remember what they poop out. I'm not a biologist. I don't care. What I do know is that what they poop out is like inert and not harmful to the environment, right? So they can process the oil. Bacteria are amazing. I don't want to go down this tangent. You are amazing. You have amazing bacteria. Let's leave it at that. What are these? Does anybody know what these are? Well, they're bumps. Good job. It's not a record player. It's close. Close to a record player.
Is this the braille that you read?
No. Now we're getting better. Okay. This is the modern record player, which is still now very old-fashioned because nobody uses physical media anymore, right? Okay. So you guys might still remember the difference between, say, a DVD and a Blu-ray.
Wait, there's
No? Some of you are like, look at Mr. Bailey, you are really old. You've heard of it. Something that your grandparents like keep, right? Okay. Which one's better, Blu-ray or DVD? Blu-ray. Why is Blu-ray better? Because it says so. It says Blu-ray on it. Right? DVD, digital video disc. Blu-ray just means blue light. So DVDs use infrared wavelengths of light to store the information on the physical disk. If you zoom in on that physical disk, you'll see structures like this. You'll see little bumps on it. Okay? What sort of thing do you need inside of the DVD/Blu-ray player in order to read the disk? Lasers, right? Lasers like bacon make everything better. Sorry for my non-pork eating friends. So these pits, this is what they're called. They're called pits, even though they're really bumps. These pits or features on the disk are read by a laser. The laser comes in, strikes the surface, reflects off the surface, and the way that the computer in the player knows whether or not a 0 or a 1 is being read is because of thin film interference. In this case, it's not so much a thin film, but rather the edge of a pit. The feature size, the height of one of these pits on the disk is determined by the quarter wavelength of the light that's being used to read the information. Because a quarter wavelength difference, right? If this incident laser beam comes in, and one beam comes in and bounces off, but the next one goes into one of the pits, or next to a pit. I know it's really confusing. The pit terminology doesn't make any sense. I did not make this technology, okay? But if it gets to the edge of a pit, then it has some extra path length to go through. And over here in the reflected beam, there's a sensor that's reading that beam. And if part of the laser is hitting a pit and part of the laser isn't, then those two waves are 180 degrees out of phase, and the detector will see no laser light. However, if the incident laser beam is on a pit, right, and it just bounces off of a pit, or it just bounces off of a trough, okay, then the laser detector will see the constructive interference from those two beams. And so basically what the detector sees is bright and dark flashes. So what's a bright flash? It's a 1. And what's the dark flash? It's a 0. And now you got a string of 1s and 0s flying off the surface. What do you have? Whatever movie you want to watch. Whatever sound channels you want to have, right? And all that kind of stuff. Notice I said the feature size depends on the quarter wavelength of the light that's being used. In a DVD, that's infrared light. In a Blu-ray, it's close to ultraviolet light. Which of those has a higher frequency? I keep talking about frequency, and we really should talk about this really quick. What are the colors of the rainbow? Roy G. Biv. Have you guys heard Roy G. Biv before?
Yeah.
No? Okay. They Might Be Giants. The album name is Here Comes Science. There's a song on there about Roy G. Biv. Roy G. Biv was a colorful man. The colors of the rainbow held in his hand. Go listen. It's a good song. What does Roy G. Biv stand for? Red, orange, yellow, green, blue. What's indigo?
It's like blue.
The thing I remember is, hello, my name is Inigo Montoya. You killed my father. Prepare to die. What was that from? Thank you. Classic film. All right, you're getting a bunch of homework. Go listen to They Might Be Giants, Here Comes Science. Go watch The Princess Bride if you haven't seen it. You have not lived till you've seen The Princess Bride. Okay. Why are you smiling? Okay, well, there's plenty of quotes from that movie I could go. Okay, red, orange, yellow, green, blue, indigo, violet. So indigo is the color between blue and violet. Newton didn't even really know what he meant by it. Okay, so which of these in this portion of the visible spectrum corresponds to high frequency, small wavelength? It's the blue, indigos, and violets. Okay? These are your high frequency, low wavelength. Yes, low wavelength light. Okay? Whereas the other end is a low frequency, high. I should not use high and low for wavelength. We usually use short and long. High frequency, short wavelength, long, low frequency, long wavelengths. There we go. Okay? So, DVDs use light that is in the infrared portion of the spectrum, so below red. Okay? Blu-rays, based on the name, use what color? Blue, indigo, violet. Actually, kind of borderline ultraviolet. Okay? And I told you that the feature size depended on the quarter wavelength of the light that's being used to read the disc. The shorter your wavelength, the smaller the feature size can be, and therefore the more information that can be stored on the physical surface. DVDs can't store as much information because of the light that is used, that infrared light. Whereas Blu-rays can store a lot more. A DVD can store about 4.7 gigabytes of information, depending on if it has multiple layers. There's some tricks you can do with DVDs, as well as Blu-rays. A Blu-ray, which is the same physical size of disc, can store over 32 gigabytes of information. And as far as visual fidelity is concerned, the resolution, whether it's 4K or 1080p, the compression that has to be done, the amount of audio tracks that can be put on the disc, right? All of that comes to amount of storage on the disc, which is why Blu-rays can be higher resolution, more audio tracks, less compression artifacts, right? So when I watch Lord of the Rings by Peter Jackson, and I pull out my Blu-rays, it's like on, what is it, on like 16 Blu-rays or something like that. Okay? They could have put all the movies on one Blu-ray, but they would have had to really compress all of the information. What they decided to do instead is they decided to put it on multiple physical discs so that they could have the greatest fidelity that they could in the presentation of the movie. That, and they understood that people like me are going to need a potty break 3 hours into the movie, right? So it's a good thing to get up, have to change the disc, stretch, go to the bathroom, get some more popcorn. Those are long movies, but man, do I like them. All right. Before we leave the topic of thin films, allow me a trip down memory lane. This is totally applicable. This is not a distraction. I was in my undergrad, and I was joining the optics team because they were experimentalists, and I liked what they were doing, and optics is fun. And we were sitting around going, okay, what are we going to do? What are we going to research? When a couple of my advisors had gone to a conference and came back. And they sat us all down, all of us students, undergraduates, graduates, they sat on the research team, and they sat us all down, and they said, we have an opportunity for you. We're like, this sounds like homework. They said, well, sort of. We've been contacted by Southwestern Research Institute, MIT, and I can't remember the other, University of Arizona at Tucson. And they want us to build a mirror coating for an X-ray telescope. We're like, okay, we know how to do that. And then they started telling us like what part of the X-ray spectrum and what it needed to do. And I won't bore you with the technical details. The short version is they wanted to take a picture of the Earth's magnetic field. Yeah, what does it look like? What's a magnetic field? Thank you. They're invisible, aren't they? So how do you take a picture of one? Find the Ghostbusters. No. You take a picture not of the field, but what's trapped in the field. And what's trapped in the field? Us, thank you. Charged particles coming from the sun, right? So we can get a picture of the magnetosphere of the Earth, the magnetic field and the regions surrounding the Earth. We can get a picture of the magnetic field of the Earth if we can take a picture of the charged particles that are trapped in the Earth's magnetic field. We're like, great. Why are we doing this? Interesting scientific problem, but quite frankly, I've got a lot of homework to do, right? And am I just going to get a pat on the head for we're all Americans. What's in it for me, right? And they said, well, if we can pull this off, then your graduate school is paid for. You see, what had happened is MIT, University of Arizona at Tucson, and the Southwestern Research Institute had gone to all of these companies that specialize in X-ray mirrors. Little tiny companies, you probably haven't heard of them. Intel, AMD, Motorola, TSMC. What do all these places have in common? What do they make? Chips. Well, Intel does. Well, let's not talk about Intel. They make chips. And the way that they make chips is through something called photolithography. Lithography is a machine that uses light and a masking technique to kind of burn the pattern of the chips into the silicon. Okay? And as chips got more and more powerful, smaller and smaller and smaller, the feature sizes, the transistor sizes had to get smaller and smaller. They had to, I just cleverly erased it, they had to get down to more and more like ultraviolet types of the ends of the spectrum, and they were working their way into the X-ray. Beyond ultraviolet lies the X-ray region of the spectrum. They were working their way in there. They needed X-ray lasers, they needed X-ray mirrors, and in our research, we specialized in the extreme ultraviolet / soft X-ray region of the electromagnetic spectrum. And we're like, paid? What? Graduate school? I'm on. Like, who cares, right? It turned out that they gave us a close to impossible problem to solve. The mirror that they wanted had to do two things. It needed to constructively interfere with a certain wavelength of light and destructively interfere with several others. Sunlight is a mixture of all kinds of things, but what they wanted to study was a very faint signal in a very bright electromagnetic spectrum. And so what we had to do in a single mirror, so we couldn't pull these, opticians have a whole bunch of tricks. We're like, oh, just use a lot of mirrors. You can cancel whatever you want. It could only be a single mirror because of the intensities that we were talking about. So in a single surface, we had to do a constructive interference and we had to have a anti-reflective mirror for a lot of different wavelengths, and in the same mirror have it be a completely reflective surface. Yes?
Did it have to be like thin film, or could it have been like glass, water, glass?
Okay, X-rays go straight through glass. Water is not something you want to put on a spaceship, satellite. Okay? So the design limitations are starting to come in. Okay? So we sat down. We said 18 months. We can do this in 18 months. Turns out it took us 24. But that's okay. MIT, it took them like 4 years to do their part of the project, so we were faster. So what we came up with, by we, I mean like the 10 or 12 people that all worked on this, our advisors, us as undergrads who then became graduate students, right? And we just shifted from one side of the desk to the other, I guess, as we came through. We got our bachelor's degree. They patted us on the head and said, keep working, right? So what we came up with was a multi-layer thin film structure. So what we were doing is we were bouncing off like different layers, right, at various angles and things. It was very complicated. And we had the theorists were doing all of the math and computer coding to try to model, like, see if we can make it work in the computer. And I was part of the manufacturing and deposition side of it. So I was in charge of making sure that we could actually build the darn thing. Like, the theorists can dream up whatever they want, right? But if we can't actually make it happen, it's not useful, right? And then we had a characterization team that would figure out if what we had made was actually what we thought we had made, right? And this is the point where we were developing skills of like being able to lay down like atomic thick layers. Like we got to the point where I could dial in. I was like, how many atomic thicknesses, atom thicknesses of uranium do you want on your surface? Or silicon or whatever. Give me something, I can lay it down. It's a process called sputtering. It's really fun. And so we worked on this. There was a lot of us working on it. And we eventually got to a point where we discovered that we needed uranium and silicon interleaved layers. And we had to change the thicknesses, okay, as it went, right? And we were trying to like pull, and we couldn't figure out how to get destructive interference for a very specific wavelength. It just wasn't working. We tried 3 or 4 materials in the layer, and that didn't work. But science is the art of trying over and over and over again, failing until you make it happen. We couldn't make it happen. We were getting to the 24-month mark, and we're sweating bullets, and they're like, are they going to take away our graduate degrees, and they're not going to pay us any money, and whatever, all this crap, right? And so one day, the characterization team decided to kind of go back to a previous one that we had done about 6 months earlier. And they were like, this one showed promise. Let's recharacterize it. Let's see what's going on. So they threw it into their equipment to characterize it. And lo and behold, one of the samples that wasn't working before all of a sudden was working. And we're like, okay, you got to understand that success in science is mostly about luck. You do a lot of hard work, but then you get lucky, okay? One of my friends who was a writer said it takes about 10 years to become an overnight success, right? Like it takes a lot of hard work before you finally achieve something, right? And so we're like, what the heck's going on? And what we discovered is that an oxide of uranium had formed on the very top surface because it had sat for a while. And that oxide was the one that we needed in order to cancel that last little bit of light. That project is called the IMAGE satellite. It's a imager for magnetosphere observation, and Aurora. I can't remember what the acronym stands for anymore. NASA is really famous for their acronyms. But that satellite launched in 2000, and I graduated in 2001. I was present for the launch. It launched from Vandenberg down here, California. And I remember standing there with a bunch of doctorates in physics, and they were all saying, so what did you get your doctorate in for this? I was like, dude, I don't even have my master's yet. I'll get that next semester. And they're like, well, what are you doing here? I was like, I did the mirror part. They're like, oh, you did the mirror part? That worked really well. We're like, oh, thank you. Yeah, it did. And I'm, of course, sitting here on the launch pad sweating bullets because what I'm thinking is there going to be 2 big Dave Balogh thumbprints when they first turn on the camera, right? Matt and Shannon, the other team leads, were like, you did clean it, right? It's like, yes, multiple times, right? So anyway, we were having a good time, and they're saying like, yeah, I did my doctorate on the little tiny piece of wire that connected the thing, and we're like, we went and found our advisors. I was like, where's our PhD? Right? These people are getting PhDs for connecting wires to stuff, and we had to pull off the impossible. What's going on here? They're like, you want a PhD? We got another problem for you. So, yeah, I mean, it's amazing how a part of your life can really come down to what amounts to an accident or a mistake or something you weren't expecting, right? But it'll work itself out in time. I, of course, spent way too much time telling you about my life, and so I will finish up chapter 27 on Monday, right, in lab. It's going to be lecture. I'm not going to have to do it for 2-3 hours, right? So when I'm done after probably about 60 minutes, you can stay, get help on your homework, whatever, right? Monday's a really good day for grass, getting things tightened up, because what are we doing next Tuesday? Review for the exam that happens on. If I don't see you in grasp, have a great weekend.